Problem number 12.83, and that's a problem of the diesel engine now. The diesel engine has got the inlet at 95 kilopascal and 300 Kelvin and a compression ratio of 12:1. The combustion release 1300 kilojoule per kg of the heat. Find the temperature of the after the combustion using the cold air properties. If you can say like the find the temperature of the after the combustion. So if you can imagine the diesel engine, so we have got the four processes in diesel engine. From state 1 to 2 we have got the adiabatic compression. From 2 to 3 we have got the constant pressure heat addition over here. From 3 to 4 we have got the adiabatic expansion or reversible adiabatic, which is also the isentropic expansion. And from 4 to 1 we have got the constant volume heat rejection. So it's a like find the temperature at the end of the combustion, which means like we need to find the temperature T3 over here. Using the ideal gas equation or using the air equation. So the initial state is given, which is 95 kilopascal and 300 Kelvin, and the compression ratio is given, which is 20. The combustion release the heat from 2 to 3 is already given. So need to find out the temperature at the end of the combustion. So from state 1 to 2 we have got the adiabatic compression. So we need from moving from 1 to 2 we can find the property at state number 2. At state number 2 temperature, which is actually from which is equal to T2 by T1, that is equal to V1 by V2 raised to power K minus 1 over here. So T2 would be equal to 300 multiplied by obviously the compression ratio raised to power K minus 1, as already for the air we are assuming the value of K as 1.4. So we have got the temperature T2, which is equal to 994 Kelvin. Now need to find out the heat transfer, oh sorry, the work done. Do not need to find out the work done, but we need to find out the maximum temperature. So the process from 2 to 3 is constant pressure heat addition. So for the constant pressure heat addition, we reminding the previous lecture. So from 2 to 3, if we have got the constant pressure process, in a constant pressure process, the heat transfer is equal to change in enthalpy, which would be equal to H3 minus H2 over here. So enthalpy equation for the ideal gas, that is Cp delta T, but for the gases you can use the Cp delta T. So from 2 to 3 we have got Cp delta T, and that is equal to Cp T3 minus T2 over here. So Cp for the air is equal to 1.004. So the process from 2 to 3 is constant pressure heat addition. From 2 to 3 the heat is already been given, which is 1300 kilojoule per kg. Cp for the air is 1.004. T2 already been found, and that is equal to 994.4. So we need to find the temperature T3. So rearranging this equation, and you can just put the value of each and every known thing, and so the temperature T3 would be equal to 2289 Kelvin. So that was the only thing which was required in this question. Moving next to the problem number 12.86 of the same book. A diesel engine has got a compression ratio of 20 to 1 with an inlet of 95 kilopascal and 290 Kelvin, which is definitely at state 1, with a volume of 0.5 liter. The maximum cycle temperature is 1800 Kelvin. Find the maximum pressure, the inlet specific work, and the thermal efficiency. So over here again we need to find the temperature the maximum temperature T3 over here. We need to find out the specific work, and we need to find out the thermal efficiency. So moving from state 1 to 2, we have got isentropic compression. For the isentropic compression, we have got the temperature T2 would be equal to T1, V1 by V2, that K minus 1, and just putting the value, and you can find the temperature T2, which is equal to 961 Kelvin. For the pressure P2, we can use the equation, which is P2 would be equal to P1 V1 by V2 raised to power 8. So that means P1 is already been given, which is actually 95 kilopascal. The V1 by V2, which is the compression ratio, is already been given, which is 20, and K is 1.4. Just putting the value, you can find the pressure, which is equal to 6,297.5 kilopascal. For the volume V2, volume V1 can be found out using the equation PV is equal to RT. So that one P1 V1 is equal to RT1. V1 would be equal to RT1 divided by P1, and that is V1. So you can use like V1 is equal to RT1 divided by P1. That's it. Yeah. So V1 by V2 is equal to 20. So putting them equation, and you can find the volume V1 and also the volume V2, which is what volume V2 is over here. The work done in a constant pressure process is equal to, sorry, not the constant pressure process, but the adiabatic process from state 1 to 2 would be equal to uh, U2 minus U1, as there is the heat transfer from the first law of thermodynamics. Heat transfer would be equal to 0 for the isentropic compression or the adiabatic compression. So from state 1 to 2, we can find the work done, and the work done would be CV delta T, and that is equal to 481.1. And obviously that's a negative work. Once we have got the equation done, that this work would be needed to be, for the network, this work need to be subtracted from the total work. At the combustion at constant pressure, which is the maximum pressure, so P3 would be equal to P2, which will previously been found out, which was equal to uh, somewhere here, which is 6297.5. Now for the volume V3, so we have got, again, using the simple equation, PV by T would be to constant. So if I've got the pressure constant, so V by T would be a constant, and V3 by V2 would be equal to T3 by T2. Putting the value of V2, which been found out over here, that's why we have found out over here in this equation. Then we have got the T3, which been already been given. Sorry, that was actually some mistake over here. I've said it is 1800 Kelvin. The peak temperature been already been given. 1800 is there. T2, which was found out somewhere here now 961 Kelvin. So putting the value, we can find out the volume V3. So once we have got the pressure P3, volume V3, we can find out the work done from 2 to 3, which is equal to, the work done from 2 to 3 would be equal to the pressure, which is constant, is 6298, V3 over here minus V2, which is over here. So you can find the work done. So the net work obviously would be equal to the this work minus that work. So later on we can check it. The heat transfer from from 2 to 3 would be equal to, using the first law of thermodynamics, the heat transfer will be equal to change in internal energy plus work done. Uh, yes, you can use the change in internal energy plus work done, but also you can use the equation which actually we've already said earlier, like the heat transfer in a constant pressure process is equal to change in enthalpy, which is equal to H3 minus H2. So that is also equal to Cp delta T, and Cp for the air is equal to 1.004. T3 is already there, T2 is already there. So yes, if we have got already temperature, so you can use simply equation, and that is from the heat transfer from 2 to 3 would be equal to 842.4 kilo joule per kg. For the temperature T4, the process from 3 to 4 is adiabatic expansion, and that is T4 would be equal to T3 V3 by V4 gamma minus K minus 1. So T4 would be equal to 3 T3 V3 by V4. So we have already got the volume V3, which is over here. We have already got the volume V4, which was initially given as 0.5 liter. I just convert into the cubic meter, and that is or even we have already got the volume V1 somewhere, so you can just equate them with the volume V4 as V1 is equal to V4. Then just putting the value, and then you can find the temperature, which is equal to 698 Kelvin. The work done, which is from T to 4, would be again an adiabatic expansion. Adiabatic expansion, that would be CV delta T, and putting the value of T3 and T4, CV for the air, you can find the work done, which would be equal to 790.1. Now, once we have got all the work done, so the net work, which actually the net specific work would be equal to work done, which was from 1 to 2 adiabatic compression, the work done, which was from 2 to 3, which was constant pressure work done, and work done, which was from 3 to 4, which was adiabatic expansion. We do not have got any work done from 4 to 1 because the process is constant volume process. So adiabatic work done would be the negative work, it would be positive work, and this would be the positive, as the compression is the negative work. So from 2 to 3, we have got the work done. Sorry, from 1 to 2, we have got the work done. From 2 to 3, we have got, and from 3 to 4. Putting the value which we have already got, so 241.5 from 2 to 3 plus 790.1 minus the work done, which was from 1 to 2, that equal the net work in the cycle equal to 550.5 kilojoule per kg. The net efficiency would be the net work divided by the net heat supply, and that is equal to 65.3%. This was the problem for the diesel engine. So these are the basic problem. Yes, we have done the A standard auto cycle and A standard diesel cycle. For the normal auto cycle and diesel cycle problems, we need to find the heat transfer from the combustion equations, and there are some other complexity as well. Thank you very much. Hope you understand the diesel cycle and auto cycle.